Hello and welcome to lecture number 38 of the course Theory of Computation. In lecture number 37, we saw that ATM is undecidable. Right? So the acceptance problem of given a Turing machine M and a string W, does M accept W? This is not a decidable language. Right? This is not a decidable problem. Sometimes we also refer to it as a halting problem, and we said that the real halting problem, which is given M and W, does M halts on W, right? Does M halt on W? This is also an undecidable problem, right? This is also an undecidable problem. Halt TM, right? In this lecture, we'll just define Co-turing Recognisability and say a few remarks, and which will close off the fourth chapter in the book, right? So let's define Co-turing Recognisable. So a language is said to be Co-turing Recognisable if its complement is Turing recognizable, right? So whenever this prefix co is there, it means it has something to do with its complement, right? So A is Co-turing Recognisable if a complement is Turing recognizable, right? Which means there is a Turing machine M that recognizes the complement of A, right? Now what does it mean? It means, so consider the Turing machine M that recognizes the complement of A. So when X is in a complement, or which means when X is in not in A, M accepts X, right? When X is in a when X is not in a complement, meaning X is in A, right? Then M. So what we know is M recognizes a complement. So whenever X is in a complement, M must accept X. Whenever X is not in a complement, M should not accept X, right? But then should not could be two possibilities. We are not saying that M should be a decider. So M can reject X, or M can loop on X. So these two possibilities exist, right? M can reject X or M can loop on X. So there must be some strings in A, right? So whatever is not in A complement is in A, that M may be rejecting, and some strings in A that M may be looping, right? So in other words, so now if you take M and flip its output, right? So all the strings that are in A complement will be rejected. All the strings that are in A need not be accepted, because there could be some strings in A that could be again be looping, right? So that's what I'm saying here. We can flip the output of M to get a Turing machine M prime, right? So M prime will always reject when given a string in a complement, right? Because whenever M is given a string in a complement, it accepts. So whenever M prime is given a string in a complement, it will certainly reject, but it need not accept every string in A, because M need not reject every string in A. M may loop on some strings in A, right? So in other words, what I am saying, maybe very quickly I can draw a figure. So there are three types of strings, right? So this is A complement, this is A, right? So in A complement, all the strings M accepts, right? M accepts. In A, there are strings that M rejects, and there are strings that M loops, right? So these two together form A. Right? These two sets together form A. Now the point is that when we flip the output, this accept will become reject, and this reject will become accept, but the loop will remain loop. So that's why I am saying that for M prime, it is not, the language recognized need not be A, it is some subset of A. But all the strings in A complement will certainly be rejected, right? Anyway, so co-Turing recognizable means that the complement must be Turing recognizable, right? So one of the interesting theorems is that a language is decidable if and only if the language is Turing recognizable and is also co-Turing recognizable, right? So A is decidable if and only if it is Turing recognizable and co-Turing recognizable. So let's see the proof on why this is true, right? So this is an if and only if statement. So we need to prove both directions. So first we will prove the forward direction. Suppose a language is decidable, we will show that it is both Turing recognizable and co-Turing recognizable. So suppose it is decidable, suppose A is decidable, right? Which means there is a decider for A. Let's say the decider is M, okay? Which means the language recognized by M is A, right? So M is also a recognizer for A. That's it. Now we have to show that A is co-Turing recognizable also, right? M is a decider for A, so M always halts, which means M accepts all the strings in A and rejects all the strings not in A. So we can take M and flip the output of M, right? So it will always reject strings that are in A and accept strings that are not in A. So in fact, if you flip the output of M, you will get M prime, which is a decider for A complement, right? So a decider for A complement will also be a recognizer for A complement. Hence A complement is Turing recognizable, right? Which means A is co-Turing recognizable. So the decider for A, if you flip the output, you get a decider for A complement, which is a recognizer for A complement, which means A is co-Turing recognizable. So the forward direction is complete. If A is decidable, the decider for A serves as the recognizer for A, and if you flip the output, you get a recognizer for A complement. Now the other direction is, if a language is both recognizable and co-Turing recognizable, we have to show that it is decidable, right? So suppose A is both recognizable and co-Turing recognizable, right? So what does it mean? It means that there is a recognizer for A, there is a recognizer for A complement, right? They need not be related machines, so there could be two different machines, right? So let's say M is the recognizer for A, which means M is a Turing machine that accepts all the strings in A and does not accept any string that is not in A. Again, it may reject or loop on the strings not in A, right? Because it need not be a decider. Similarly, let M prime be the decider for A complement. It accepts all the strings in A complement. It may reject or loop on the strings that are not in A complement, right? Or which, in other words, that are in A, right? So now using these two recognizers, recognizer for A, recognizer for A complement, we can build a decider for A, right? So the decider is very simple, right? What we will do is we will run M and we will run M prime both in parallel, right? So on the same input, we will not do the mistake of running one completely and waiting for the end. Instead, we will run in parallel. We will run one step M, one step M prime, and so on, like so that it's like both of them progress in computation, right? The point is this: given any string, it's either in A or in A complement, right? Because A complement is just defined to be everything that is not A, right? So given any string, it is either in A or in A complement. Suppose it is in A, right? So given a string W, suppose it is in A, which means we know that M accepts it, right? Because M is a recognizer for A, so we know that M must accept W. If it is not in A, which means it's in A complement, we know that M prime accepts that, right? Because M prime is a recognizer for A complement. So if W is not in A, W must be accepted by M prime. So given any string, either it has to be accepted by M or it has to be accepted by M prime. So we run M and M prime in parallel. At some point, one of them must accept, right? So if M accepts, we accept, right? It's a string in. So we want a decider for A. So we want all the strings in A to be accepted, all the strings not in A to be rejected. So, and we know that any string that is given as input is either going to be accepted by M or going to be accepted by M prime. So if it is accepted by M, we accept, right? Because it's a string in A. If it is accepted by M prime, it has to be a string in A complement, then we reject. And one of this must happen, because both every string is either in A or A complement. If it is in A, M should accept. If it is in A complement, M prime should accept, right? So running these two machines in parallel, one of them must accept, and if depending on which one you accept, which one is accepting, we say it is in A or A complement. So this is a decider, because whether it is in, regardless of whether it is, if it is in A, it is accepted. If it is not in A, it is rejected, right? So we are combining a recognizer for A and a recognizer for A complement to build a decider for A, right? So again, just stating the result is again that a language is decidable if and only if it is both Turing recognizable and co-Turing recognizable, right? So decidable if these two are satisfied, and if these two are satisfied, then it has to be decidable. So finally, some minor observations using this theorem, right? So we saw at the beginning of lecture 37 that ATM is recognizable, right? So this Turing machine that we talked about, U, this is a recognizer for ATM, because whenever M accepts W, it's a yes instance of ATM, U accepts that pair. The issue happens when M loops on W, right? So ATM is Turing recognizable. We have shown that ATM is undecidable, right? So if ATM is co-Turing recognizable as well, right, or in other words, if ATM complement was also Turing recognizable, both ATM and ATM complement will be Turing recognizable. This would imply that ATM is decidable, but we know that ATM is not decidable. So we cannot have both ATM and its complement being recognizable. Let me repeat. So the theorem that we just saw said that a language is decidable if it is both recognizable and co-Turing recognizable, right? So we know that ATM is recognizable. If ATM complement is also recognizable, that would imply that ATM is decidable. We know that ATM is not decidable. So that should mean that necessarily ATM is not co-Turing recognizable, which means ATM complement is not Turing recognizable, right? Because if ATM complement was Turing recognizable, it will imply that ATM is decidable. Hence, we can infer that ATM complement is not Turing recognizable. So this is the first time we are seeing a specific language and saying that this is not Turing recognizable. ATM was decidable, but ATM was undecidable, but it was recognizable. So here is a language, the complement of ATM, which is not even recognizable, right? Finally, one couple of more points. We asked if, or we mentioned that EQ-CFG is not decidable, right? And we are saying that EQ-CFG is co-Turing recognizable, meaning the complement of EQ-CFG is recognizable. So why is it recognizable? So if you just to remind ourselves, EQ-CFG is like you are given A and B context-free grammars. So given A and B is LA equal to LB. Are they equivalent? This is the question. So if they are not equivalent, right? So I am talking about co-Turing recognizable. It's a no instance. Suppose it's not equivalent, we can just run through all possible strings, and there has to be some string that is accepted by A or generated by A but not generated by B, or vice versa, generated by B not generated by A, right? So you just run through all the strings starting from the empty string, then string of length 1, string of length 2, and so on. At some point you will find a string that is accepted by one but not by the other, right? If they are not equivalent, you will find such a string. So that's why the complement of EQ-CFG, right, the no instance when A and B are not equivalent, is Turing recognizable. In other words, EQ-CFG is co-Turing recognizable, right? So the complement of EQ-CFG is recognizable, which means EQ-CFG is co-Turing recognizable, right? So by this process. And I mentioned earlier that EQ-CFG is undecidable. Right now we are not going to prove it, but right now let's take it as a fact. Now EQ-CFG is undecidable, but it's also co-Turing recognizable. If it was Turing recognizable, that would imply that because it is Turing recognizable and co-Turing recognizable, it is decidable. But we know that it is not decidable. Hence, it implies that EQ-CFG is not Turing recognizable. Right? Maybe I'll explain again. If EQ-CFG was Turing recognizable, then theorem 4.22 implies that EQ-CFG is decidable, which we know is not the case. Hence, EQ-CFG is not Turing recognizable, right? So that's the last point that I want to say. So just to recap what we saw in lecture 38, we defined co-Turing recognizable. A is co-Turing recognizable if a complement is Turing recognizable. Then we showed this theorem that a language is decidable if it is both recognizable and co-Turing recognizable. And using this, we inferred that, we saw the proof. Using this, we inferred that ATM complement is not Turing recognizable, or in other words, ATM is not co-Turing recognizable. Right? So maybe I'll just write that here. ATM is not co-Turing recognizable, and similarly we saw that EQ-CFG is not Turing recognizable because it is co-Turing recognizable and undecidable. And that's where we end lecture 38. This is also the end of week 7's content. This is also the end of chapter 4 in the book. So in chapter 4 and in week 7, so week 7 was just entirely chapter 4. We saw decidable languages using regular languages, decidable languages using context-free languages. We saw the theory of countable and uncountable sets. We saw undecidable languages, right? We saw that ATM is undecidable. We saw the proof for that. And now we are seeing some other results about co-Turing recognizable and Turing recognizable as well, right? So this completes chapter 4 and also week 7. In chapter 5, which we will see in week 8, we will see reductions, which is a way to transform one problem to another. So and because one of them is easy, the other problem is easy, and because one of them is hard, the other problem is hard. You can make inferences about the relative difficulty of these problems using these transformations. So at some point we had seen some aspect of these transformations earlier. At that point I had indicated. These are called reductions. So we will see that in chapter 5 and as well as week 8. As far as week 7 is concerned, this is it. So see you next week.